Hi guys, so today we're going to be doing differential equations. So for differential equation 1, we're given dy over dx is equal to y squared plus 12 times cosecant squared x over y. So the first thing we're going to do is take the integral of both sides by having the y's on one side and x's on the other. So as you can see, from the right hand side, I just multiplied the y, so that y is the numerator on the left, and I divided the y squared plus 12 from the right, so it's in the denominator on the left. And then on the right, I just took the integral of cosecant squared x. But in order to solve this, we need to do u sub. So I said u is equal to y squared plus 12. Then you take the derivative of that, and you get 2y dy. And then when you plug in du is equal to 2y dy, you can factor out a 1/2, and you're left with the integral of 1 over u du, which is equal to the negative cotan x plus c1. We'll get into why I denoted that as c1 later on. So the integral of 1 over u is ln of u, which is simply ln of y squared plus 12. And don't forget to multiply that 1/2 on the outside. And that's just going to be equal to negative cotan x plus c1. And then I just multiplied the 2 from the left to the right. So I end up with ln of y squared plus 12, which is equal to negative 2 cotan x plus 2 c1. And then the final answer is ln of y squared plus 12, which is equal to negative 2 cotan x plus c. And you don't need to solve for y in this case. I wouldn't really do anything else to this problem except for leave it like that. And the reason why you want to have c1 and not just c as all the constants throughout, because you want to show that the value of the constant changes. So usually you end up with a final c, and that's the final c is just not going to have any subscript to it. But everything before that, if the c changes in value, you would denote it as c1, c2, c3. Here, the c1 value only changed once, and that was after we multiplied the 2 to it, which is why it just turns into the final c. So for the second differential equation, we're going to be solving for y. So we're given that y prime is equal to y minus 3 over x. So first I'm just going to convert y prime into dy over dx. And then I'm going to move the x's onto the same side and the y's on the same side. So here that's what I did, and I just took the integral of both sides. So then, after taking the integral of 1 over y minus 3 dy, I'm left with ln of absolute value y minus 3. The reason why we have absolute value there is simply just because we can't guarantee that it's going to be negative. Because if you put in like a 1 for y, it'll be negative 2. So in order to ensure that it stays positive, you're going to need to have absolute value signs around y minus 3. And then on the other side, you have ln of x. Again, you don't know the number for x. So you're going to need to have an absolute value sign to make sure it's positive. Then you're just going to add the c1. And that's similarly what we did in the first problem. So then I put e to the ln of y minus 3, which on the left is just the absolute value of y minus 3. On the right, it's e to the ln of absolute value of x plus c1. But e to the ln of something cancels out, so I'm just left with absolute value of x on the right. And I multiplied, I split the e, ln of x plus c1 into two different products. So e to the c1 is multiplied by the absolute value of x. Then I just got rid of the absolute value signs because we do not need it anymore. And I put the plus or minus sign on the right side just to show that we got rid of the absolute value sign. And then basically you can notice how the c changes from c1 to c because the value of e to any constant changes the value of the constant. So we're just going to keep that as final c. And then you're just going to add 3 to the right, and that is your answer because we just solved for y. So for differential equation number 3, we're going to solve for y. So we're given that xy is equal to y prime minus x. So the first thing I'm going to do is I'm just going to add the x to the left side. So xy plus x, which is equal to dy over dx. Then I'm just going to factor out an x. So I'm going to have x times y plus 1, which is equal to dy over dx. And then I'm going to take the integral of both sides. I'm left with ln of absolute value y plus 1. Again, we can't guarantee if the quantity is going to be positive or negative, so we need to have the absolute value signs there, which is equal to x squared over 2 plus c1. And I just switched the side that they're on. That doesn't really matter. That's just more of my preference. So then what I'm going to do is I took e and I did e to the ln of y plus 1, which cancels out, which is why on the left all you see is absolute value of y plus 1. But on the right you have e to the x squared over 2 plus c1. Since they have the same base, I can just split up e to the c1 and e to the x squared over 2 into products. And on the left side, I got rid of the absolute value signs. So that's why we have the plus or minus in front of e to the c1 power. Since the value of the constant now changes again, because e to any constant will change the constant's value, we're going to just get rid of the c1 now, and we're just going to have the final c, no subscript. And then you're just going to subtract the 1. So you're going to be left with y is equal to c times e to the x squared over 2 minus 1. So for differential equation number 4, we have x times y cubed, which is equal to negative e to the negative x squared times dy over dx. So I'm just going to move the x's on the same side and the y's on the same side. So we're left with x over negative e to the negative x squared power times dx, which is equal to 1 over y cubed dy. And that's just rearranging. Then on the left-hand side, I'm just going to take out that negative 1, and I'm just going to put it outside the integral. And then I'm just going to have the integral be x times e to the x squared, because in the denominator, since there was e to the negative x squared, it'll just become e to the x squared because it's in the numerator now, times dx, which is equal to the integral of 1 over y cubed dy. Then we need to do u sub, because we have that e to the x squared, so u equals x squared, and then I took the derivative of that, which is 2x dx. So since we set dx equal to du over 2x, the x's cancel out, which is shown here. And then you're just going to factor out that negative 1/2. And then you're left with negative 1/2 times the integral of e to the uth power du, which is equal to the integral of 1 over y cubed dy. So when taking the integral of e to u, it's just going to be e to u. And then plus c, which is equal to negative y to the negative second power over 2. And then I just substituted x squared back in for u, so you're left with negative 1/2 times e to the x squared plus c. It's going to be equal to negative y to the negative second over 2. Find the equation of the graph that passes through the point and has the indicated slope. Solve for y. Point 2, 4, slope dy over dx equals y minus 2 over x. So the first thing you're going to do is that you're just going to plug in 4 for y, which is equal to x for 2, so 2c plus 2. And then you're just going to solve for c, so 2 is equal to 2c. We did that by subtracting the 2, and then c is equal to 1. Lastly, you're just going to plug the value of c back in, since you found out it's 1. So y is equal to x plus 2. And there you have it, the equation of the graph that passes through the point and the slope. Match the slope fields with their differential equations. So for this one, just pretend that the graphs are going from A to E. So the first one would be A, and then all the way across it would be C, and then the last two would be D and E, just for the sake of this problem. So how I like to approach the slope is like to do the easier problems first. So let's do dy over dx, which is equal to 2x plus 4. If you take the integral of that, you're going to have a quadratic because you're going to have x squared over 2 plus 4x. And if you look at the graphs, there's only one graph that has a quadratic, and that is the last graph. So your answer for that one is E. Dy dx equals -5. So for here, you need to know that there needs to be a negative slope, and it needs to be steep because 5 is a number that would cause the slope to be steep. So if you look at graph D, you'll be able to find that each line at every point on the slope fields is in the negative direction and it's steep, indicating it's -5. So that one would be D. For next, dy over dx, which is equal to x minus y. When x equals y, the slope is 0. So above that line, when x is greater than y, the slope is positive. And below it, the slope is negative. So you know that that one has to be A. For y squared plus 5y, you know the slope equals 0 at y is equal to -5 and 0. Because that's when, if you factored out the y, that's what you would get for y equals. And you know for graph B, there is a horizontal line at each point that is at y equals 0 and y equals -5. So automatically you can tell that that graph would be B. And basically above and below is positive and in between is negative. And you can see that within the direction of the slope. So that one's B. And then for x squared plus y squared, the slope is always going to be positive and it's going to look vertical except near the origin. And a way to test this out is that you can just plug in points. You'd plug in a 0 for x and a 0 for y, and you would know that at that point, the slope is going to be 0, so it's horizontal. And you can kind of test that points if you don't know that the slope is always positive or that it's going to look vertical except at the origin.